All right. Thank you, everyone, for coming. We're going to get started. So thanks for joining today's robotics seminar. I'm very happy to welcome Dmitry Berenson. Thanks for coming in person. We know that it takes an effort to get out of the year and a half of just connecting and talking through Zoom. But it's great to have you here. Thanks for doing that. Sure. Dmitry is an associate professor at the Robotics Institute and EECS at Michigan University. And he directs the Autonomous Robotics Manipulation Lab, where he studies general purpose algorithms for motion planning, for perception, I would say manipulation in general, for robots to interact with the world in homes, factories, and operating rooms. Important stuff. So Dmitry, he got his PhD at Carnegie Mellon University, also at the Robotics Institute, and did a postdoc at Berkeley before starting his faculty job in 2012. We were neighbors at WPI. And he has received important awards like the NSF Career Award and the IEEE RAS Early Career Award. And I'm reading from the credentials for contributions to the theory and implementation of robot motion planning and manipulation. And I would like to highlight those two words, theory and implementation, because I think Dmitry has always had a practical mindset or a dual theory practical mindset. And it's that practical mindset that has given us important contributions in motion planning, like task space regions, TSRs, and several algorithms for constraint manipulation planning, constraint manifolds, dealing with workspace goal regions. And I would say that that same practical mindset sort of stays true to today, maybe even more practical, where today he's going to talk to us about those models that we use for planning, right? That we are happily trusting whatever they tell us. It turns out that we probably shouldn't. So how do we deal with that conundrum? When can we trust them? When we shouldn't? Thank you, Dmitry, for coming. Please, the stage is yours.
Thank you. Thank you, Alberto. So I'm very happy to be here in person. It's so great to get out of the house and off of my little corner of the world and visit other places again. I want to start this talk with a general question that I think most of the people who do robotics face at some point, which is how should you predict the effect of an action? How can a robot autonomously reason about the effects of its actions? It's one of the most fundamental questions that we face in robotics. You need it to do control, to do motion planning, to do all sorts of different things. And if we look traditionally at a behavior or some system that we want to model, what we have seen is that people are generally writing down the dynamics equations by hand. Right? So let's say I want to model how this car drives on snow, right? I would get lots of information. I'd get videos, I'd instrument the car, I'd look at accelerometers and so on, measuring what the car is doing. And then I think really, really hard, right? Because I'm trained to think about how to model things with dynamics. I think really, really hard about how to model these particular dynamics. And I come up with a bunch of equations. Right? And then I think, okay, these equations are going to be really good, right? But I can't just go with my intuition. I have to run simulations. And then the simulations may or may not work. And based on the simulations, I iterate and I update my models and so on. So this was the traditional process for getting the dynamics of a system. Still very effective today. Please don't underestimate this process. However, it turns out it's very hard to model some dynamics of some very complex systems, like, for instance, deformable objects, things like cloth and rope. Very hard to write these down by hand. So recently, it's machine learning to the rescue, right? We're going to get tons of data. We're going to get that data either in the real world, if we can afford to buy a bunch of robotic arms, or we'll get it in simulation, and we'll learn about the effects of actions from this data by using a neural network or some other machine learning method. And that is basically going to give us a function that evaluates the dynamics for a given state and control, or it'll just give us a policy directly. We won't actually know the dynamics, we'll just be able to do things in the world. Now, one thing that people miss out, of course, if you're not in this field, is that, of course, all of this stuff requires massive human intuition and engineering. So this isn't a kind of established process that we just plug in data and get policies. But even with that human intuition and engineering, we still have the same problem. We can't have perfect models for everything we want because there's just not enough data. So if you think about the configuration space of a robot arm, for instance, 7 degrees of freedom. Okay, maybe we can get enough data to cover that. But what about the configurations of all the objects the robot is manipulating? What about the shapes of all those objects, right? So it turns out if you really want to cover this space, it just becomes intractable, even with huge resources like what you see here. So I'm not just talking about theoretical limits on data, right? This is actually having a practical impact where companies are realizing, like OpenAI here, that they just can't get enough data to run fairly uninformed algorithms to do what they want, right? And they're looking for domains instead where data is more readily available. So this is not just a theoretical thing. This actually matters in practice. So I'm going to make the following proposition, at least for the purpose of this talk, that let's just assume we're never going to get perfection. We're never going to get those perfect models that we can always trust for any state and action we may want to do, or even for a broad range of tasks we may want to do with a real-world robot. So if that's really the case, then what are we going to do? Well, we have to somehow learn to live with the limitations of our dynamics models, right? And what are we going to do when our dynamics models are unreliable? We've had several different thrusts in my lab's work that have focused on this question. So one of the first we looked at was switching between multiple dynamics models inside a controller as you're doing a manipulation task. This is for deformable object manipulation. We also looked at constructing our own models that modeled specific things, not the full dynamics, but just some constrained boundary interactions. Turns out those are very useful for planning, again, for deformable objects. And what I'm going to talk about today is our work on this third thrust is learning to avoid a model's mistakes. So I'm going to talk about two specific papers, two topics within the talk today. And they have slightly different focus areas, but they have something in common too. Both of them are really not trusting their dynamics models too much. So the first part of the talk will cover our recent method on taking a learned dynamics model that's represented as a neural network and learning where we can trust that model and putting hard boundaries on the region in state action space where that model is valid. So the focus here is on providing safety guarantees so that you can guarantee that if you execute a planned accounting for the lack of knowledge of this model, you actually will get to the goal without colliding with anything. And here we're assuming the state space of the system is known. But you may say, well, that's all well and good if you have a robot arm, you know the state space, it was human engineered, it was hand designed. What about if you have an object that you haven't seen before? How could you possibly apply these methods? Well, in these kinds of domains, where we just have image observations and we don't know the state space of the object, it turns out we can still do something quite useful. But here, instead of providing safety guarantees, we're going to be focusing on data efficiency as a very important feature that allows us to scale to new tasks quickly. So I'll start with the learned model here and providing guarantees about what you can trust from that model. So this is the work of our students Craig and Glenn. These are students co-advised by me and Nechme Oze, who's a professor at Michigan. And what we observed when we used learned dynamics models was one of two things in general. There were cases when we tried to plan with a learned dynamics model of this Kuka robot, and everything kind of went well. It was trying to get to this goal, and it got there without collision. And then there were times when things, didn't go so well. So I'll just replay this. Things just went totally haywire. The arms started colliding, and it just wasn't tracking the trajectory that was planned. We wanted to understand, why does this work sometimes, and sometimes it doesn't work? And what we came up with was basically this concept that the model is going to be valid inside a trusted domain in the state action space. That outside that domain, it really shouldn't be trusted. So how do we then guarantee that we can safely reach the goal without leaving that trusted domain? That requires identifying the trusted domain, right? So I want to mention some related work. There's been, of course, a lot of related work to what I'm going to be talking about in terms of planning with uncertainty and, for instance, safe reinforcement learning. So in a lot of this work, especially the safe RL work, they're looking at similar questions, like how do we safely execute a policy or do exploration? But there's some limitations here. There's some kind of privileged knowledge about having a safe controller, at least initially, to gain data that is not really realistic for what we're looking at. And also, the GP may not reflect the true model error. It depends on kind of your kernel that you pick. Now, of course, this isn't to say that people haven't done motion planning with learned models before. In fact, we've done it. Yeah. Do you have a question?
Just a quick question. Are you assuming that the model is going to be deterministic, the actual one?
Yes, I'm going to get to that in a second, but the answer is yes, it will be deterministic. Yeah. We've definitely done some work, as well as others, on motion planning with these learned models, and we've achieved some pretty impressive results, but unfortunately, no guarantees have been provided for this kind of planning. And of course, we have to be talking also about robust control when we talk about planning and control with uncertain models, right? So there's been a huge amount of work in this area. Model predictive control with model error, reachability analysis, Russ is over there, LQR trees, contraction theory. All of these methods are basically thinking about how do I achieve a task despite having uncertainty in my dynamics. But unfortunately, there's some limitations here. They require a tight bound, usually, on the model error that you have. And where does that tight bound actually come from? Other times, you may need to have a special representation of the dynamics, for instance, a polynomial form, in order to apply a method. So in our work, we wanted to do things a little differently. And instead of having to manually specify this bound, what we want to do is estimate that bound from data and then make guarantees based on that bound. And once we have those guarantees, we can basically enforce them, enforce these bounds in a motion planner and produce a trajectory which we can guarantee will be tightly tracked in execution under the true system, even though we never know the true system's dynamics precisely. So here's a specific problem that we're focusing on here. We're given a data set of states X, actions U, and then f of xu is just the result of applying the real system's dynamics for that X and U. Again, this true system is not known, so we never have access to f directly. We just have data from it. And then what we're going to do is we're going to learn a dynamics model, which we're going to call G, from that data. And what we want to do is use that dynamics model in a motion planner to produce trajectories and then guarantee that those trajectories will get to the goal safely. Now, this is where I'm getting to the assumptions on these dynamics. The first assumption, which is the strictest, is that the dimension of the state space and the dimension of the control space are the same. This allows us to formulate a very simple feedback controller I'll show you later on. I want to say that this has also been relaxed in some follow-on work, so you don't need to have this anymore, but for the purpose of this talk, I'm going to focus mostly on this case. The second is deterministic dynamics. That will be important when we do Lipschitz constant estimation. And the third is that it's controllable. So again, that's important for our controller that we use. Some key differences from prior work, and I think the first one here is really important. There's no assumptions on the structure of G, on the structure of your learned dynamics. It can be a gigantic neural network, it can be an analytical function, it can be whatever you want, but it has to be able to conform to these assumptions up here. It's also not restricted to low-dimensional systems, so you'll see evaluations on a 6-DoF quadrotor and a 7-DoF arm. Okay, so the method has 3 parts. This is the first part where we actually learn G. And we learn G in this control affine form where we have G0 of x and G1 of x as 2 separate networks. And the networks are very simple, just a single hidden layer. We're not doing anything fancy, any amazing deep learning stuff here. We're using very standard methods to just fit these to the data that we have. So I'm not going to talk more about this. Again, standard methods just giving us this G function. But here's really the crux of the work. Once we have that G, we need to put a bound on its error, and we need to create a domain where that bound is going to be valid. And so that's going to be the majority of what I talk about in this part of the talk. And then once we have these bounds, we need to actually be able to plan trajectories with them, and we create a motion planner that can do that and outputs a trajectory that's guaranteed to be trackable on the true system. So I'll go over just briefly an outline of the main parts of the method here. So again, we're assuming we've learned G using standard methods, so we have our approximate dynamics. The first step that we need to figure out is a way to compute the Lipschitz constant of the error of the learned model from data. Right, so I'll talk about that first. Then once we can do that, we're going to determine a trusted domain for planning in which we will estimate that Lipschitz constant. And then, of course, I'll talk about how to use that in the planner. Okay, so let's start with this Lipschitz constant estimation. So again, the idea here is we want to identify the Lipschitz constant of the error between the true and the learned dynamics. And to illustrate how that works a little bit, I'm going to have this simple figure here where the true dynamics are in gold, the learned ones are in orange, the data set is in green. So you can see the learned dynamics is just a linear approximation, right? Okay, well, we can define some terms about this setup here. The first is going to be ET, which is the maximum error on the data set, okay? Then you have the trusted domain D. I'm going to talk about defining D later, so for now, just assume we have a domain D. And then we're also going to need the dispersion of our data in D. And if you don't know what dispersion is, it's basically the radius of the largest empty ball that you can fit into the data set D. Empty means it doesn't contain any of the training data. And then this is what we're going to be getting to estimate. This is the Lipschitz constant of the difference between F and G. And this is technically called a local Lipschitz constant because it's local to the domain we specify. It's not global over the entire domain of the input to the function. And if you don't know what Lipschitz constant is, it's basically a bound on the ratio of changes in the output to the changes in the input to a function. So it turns out that using the triangle inequality, we can basically come up with this bound, this epsilon, as the bound on the error between the learned and the true dynamics. And it's a function of the dispersion and also of this E, which is the maximum error on the data set. But of course, we also need to have the Lipschitz constant in order to compute this epsilon, right? So the question is then, how do we determine this LF minus G, this Lipschitz constant, inside the trusted domain? Okay, so let's start looking at this problem the way we started, which is, let's do the simplest thing first, right? So let's say we have a domain D. How do we estimate the Lipschitz constant in a domain? Well, let's sample a bunch of points in the domain, right? And this is state action space, so that's why you see always pairs X and U here. So we'll sample X's and U's, right, in this domain. We can evaluate F on those X's and U's, and we can get the error of our learned model on those X's and U's, right? And then we can calculate this ratio of the difference in error between 2 points over the distance in, over the distance between the 2 points, right? And the maximum of that error should be the Lipschitz constant, right? because the Lipschitz constant is an upper bound on this error, right? Wrong. And this is what we ran into, is that this is actually guaranteed to underestimate the Lipschitz constant, because with a finite number of samples, you're always approaching the upper bound from below, right? So you're not going to get the true Lipschitz constant in this way. So what can you do instead? Well, instead, you could overestimate the Lipschitz constant, and this will be a probabilistic overestimate for reasons I'll show you in a second. Now, why is it better to overestimate the Lipschitz constant instead of underestimate? Because the Lipschitz constant is basically saying how wrong you can expect your function to be. If you overestimate how wrong it is, you'll be more conservative. So you'll plan things that are safer than if you underestimate. If you underestimate, you are going to potentially create errors. So we definitely want to overestimate, but not too much, because we can become too conservative and then we can't do anything. Okay, so we're going to do this overestimate. How are we going to do this? We're going to apply a theorem from extreme value theory. For short, I'll just refer to it as the FTG theorem here. And what this theorem says is that in the limit, as you take samples of IID random variables and compute their maximum, you will converge to one of three different distributions, the Gumbel, the Frechet, and the reverse Weibull. Okay? So this is pretty cool, because it's saying that the maximum over these samples in the limit will actually be something you can talk about, not just an arbitrary value. Now, of these three, only the reverse Weibull is applicable in our case, because it has a finite upper limit. These others don't. We assume that the Lipschitz constant is in fact finite, so therefore this is the only distribution that actually makes sense here. Okay, so we're going to converge to this reverse Weibull distribution. How do we actually use that to estimate the Lipschitz constant? So again, the process starts out in a similar way. We sample pairs of points, we evaluate the distance between them, we evaluate the error between them, we get the ratio, right? But now, instead of just taking the max of those ratios, we fit a reverse Weibull distribution to batches of samples of these ratios. And it turns out that one of the parameters of this reverse Weibull distribution, called gamma, is in fact the upper limit. So by fitting the distribution and getting that parameter, we directly know the upper bound on the Lipschitz constant. However, we also recognize we have a finite number of samples, right? So we can't just assume that we'll have a good fit of the reverse Weibull distribution. So we have to validate our fit with this Kolmogorov-Smirnov test to make sure that the fit is in fact valid. Now, that will give us this gamma, but we want to be even safer still. We want to put a confidence bound on that gamma. So the way that we're going to do that is by basically doing a standard confidence bound on that parameter. So here, this is the inverse normal CDF. Rho here is the confidence you want to have. The bigger rho is, the bigger this number is, the bigger your Lipschitz constant is going to be. And this is the standard error of the fit, right? So we're accounting for the fit error in this overestimate. So given all this, we basically get a probability that we have a valid Lipschitz constant with a probability at least rho. Okay, here's just an animation to show you what all of this complex stuff looks like in practice. Just on a simple example, this is x squared. We're looking at a domain of -1 to 1. The Lipschitz constant here is going to be 2. And as you can see, as we take more and more samples of ratios of input to output, the upper bound here is 2, and that gamma parameter is converging, in fact, to 2. So just a numerical demonstration of this idea. Okay, so now we've got the Lipschitz constant for a given domain, but where does that domain come from? We have to figure out what that domain should be for our learned model. So there's 2 steps to determining the trusted domain. The first step is that we're going to filter out points where we have large training error. Because we learn G on a data set, we know that we're not going to get perfect error on every point in that data set. G is just not going to be expressive enough to do that. Or even if it is, it's probably overfitting, so we don't want that. So there are going to be some points where the error just tends to be higher than others. And to make our domain as big as possible, we're going to filter those out so that we can have a larger radius around the points that are left in. I'll show you what that means in a second. So we're going to filter out those higher error points. We just set a threshold and filter them out. And this is what the domain is then going to look like. It's going to be a union of balls centered at the training data of radius r. Now in this work, r is fixed. So we use a fixed r for every training data point. But you would say, well, some training data is, the fit is better than others. And in fact, that's true. So in later work, we have a varying r that varies depending on where you are in space. But for this work, r is a constant. The big question then is, what is r? And this is, you'll see where the Lipschitz constant comes in. So we have an iterative method for selecting r, this radius around the training data. We initialize it to, again, a heuristic value, and then we start to compute the Lipschitz constant, right? So an R gives us this domain, and in a domain, I just showed you a process for estimating the Lipschitz constant. So we get that in the domain defined by R. Then we check if the Lipschitz constant is greater than or equal to 1. If so, we return failure. This should look very strange, right? So I'm going to talk about that in a minute, why we do that. But let's say that's not the case, then we compute that epsilon, that error bound. Remember, that's a function of the Lipschitz constant, so now we have that, we can compute epsilon. If r is greater than epsilon, then we're basically done. We say our domain is big enough to account for the model error. We could grow it further if we want, like there's nothing stopping us from doing that, but this is sufficient. And then we return the current r. If there is, if that's not the case, then we go back to line 2 and we just iterate. But coming back to this question of Lipschitz constant greater than equal to 1, return failure, why would you do that? I mean, in principle, there's nothing special about having a Lipschitz constant of 1, right? You can have a Lipschitz constant of 2 or 5 or 20. What's the big deal? Well, it's true that in general, the Lipschitz constant can be whatever number. But in practice, for the purpose of planning, having a Lipschitz constant greater than 1 is going to create a lot of problem for us. The reason is that we need a fast way to check for the containment of a ball within our domain. Because what our planner is going to be doing is sampling a bunch of states and actions. And we need to know if we can have an epsilon ball around that sampled state and action that completely fits in the domain. Because if it exits the domain, then we could end up outside of D in execution, and the whole thing would fall apart. So we want that. So if I have this Lipschitz constant, it turns out that epsilon is going to be bigger than R, and in order to check if the epsilon ball is contained in D, we have to do a really complicated check where we are checking if one sphere is covered by multiple other spheres in some very high dimensional space, right? For the robot arm, this is 14-dimensional space. We do not want to do this kind of check in a high dimensional space. So instead, we can say, well, the Lipschitz constant should be less than 1. Then we can come up with a simple conservative check. And that conservative check is basically going to say that if the sampled state action, x prime, u prime, is within r minus epsilon of a point in my training data that I've kept, then I know that that epsilon ball fits in the r ball around that training data, right? So it's basically a conservative check that guarantees that that ball is completely contained within the domain D. So basically enforcing a low Lipschitz constant means that we can very quickly check if a point is within our domain. And in fact, the ball around that point is within our domain. OK, I've lost the video. I don't know what happened. Nope, just went blank. Maybe I stepped on a cable. Is that possible? Oh, OK. All right, I will try not to step on any cables. Okay, so this was that conservative check. It allows us to check if a ball is within our trusted domain. Yeah?
So is the picture that you have many, many data points and you subsample a small number of them, and then inside each of these yellow balls, I'm using all the other data that happen to land in that ball to verify my local Lipschitz constant. Is that?
No, this is the case that I've done my learning, I've done my Lipschitz constant, I've determined my domain D. Now I'm planning, and the planner is going to take samples, and these samples are called X prime, U prime. And I need to know how, if a ball around this sample is within my domain D that I've already computed.
I guess I was just even the yellow pictures that I'm seeing.
Okay, yeah.
They're a subset of your real data?
Yes.
You've chosen the domains around some subset of your data, and you're using the other data to do local Lipschitz approximations in each of those balls?
Yeah, that's a good question. It's not quite like that because I think it turns out we don't have enough data to do that. I mean, you could do it, but you might just get huge Lipschitz constants because you just don't have enough. Or I shouldn't say huge, you just don't have enough data to estimate it well. What's actually happening here is that once we choose a domain, we sample more in that domain to get more data to estimate the Lipschitz constant. That allows us to do independent Lipschitz constant estimation for, you'll see, multiple constants that we have to estimate too. Yeah?
Just a question. Depending on how you normalize the data, will you get a different domain?
Yeah, so in this work, we did not normalize the data in any way, so I'd have to think about if that would affect it.
Really large, and that's going to dominate a lot how do you determine the constant.
Yeah, you might be right about that. Yeah, I think you're right. That would affect it. You would have to take that into account in G. Yeah. Sorry, did you have?
In the same vein, do you do something special to compute your distances? Because I mean, your input, the domain is bigger, higher dimension than the range, and you'll have angles. And I guess if you're doing it all in joint space, it's okay.
Yeah,
but if you
right.
did have that, would you have to do something?
No, that's a great point. So, are we doing anything special to compute distances? If we were working with like fully revolute joints, or we were working with poses directly, you can argue that that's really important. Right now, this is all in Euclidean space. So even when we do have poses, we stay within a small range of poses so that we can approximate it as Euclidean. But you're totally right. The correct metric here is not Euclidean, it's SE3, a metric in SE3. Yeah. Okay. So when you're dealing with poses, I should say. Sometimes it will be Euclidean if you just have all real number degrees of freedom. Okay, so now that we've computed the trusted domain and the Lipschitz constant there, we got that bound R, and that gives us some kind of guarantee that if we stay within those R balls that we've computed around the training data, then we're going to be okay. How do we actually do this in planning? Well, the method that we propose is called Learned Models in Trusted Domains, RRT. And I really just want to point out that everything I said up until this point has nothing to do with RRTs, right? These are just general bounds that you'll get from a learned dynamics function. We used an RRT because it's fast and easy, and it's very easy to enforce this trusted domain in a sampling-based framework. You don't have to use RRT. You could use MPPI or CEM or trajectory optimization methods or PRM or discrete search. As long as you can enforce the bound that I just talked about, then you should use your favorite planner. But anyway, we used an RRT. It's technically a kinodynamic RRT, and we had to add in 2 additional checks for every state action that we generated. So the first check we have to do is we have to ensure that every XU along the trajectory that we plan is in a strictly smaller set than D. And I already talked a little bit about this with that epsilon ball thing. This is basically saying that if my domain D, right, is that outlined set out there, right, I actually need to stay in a smaller domain D sub epsilon so that I can fit those epsilon balls inside, guarantee to fit them inside for any point that I sample, right? So by staying in D epsilon and doing that nearest neighbor check, which I just described, we can guarantee that none of our epsilon ball ever leaves the set D. That's really important because in execution, we're going to wind up somewhere within that epsilon ball, but we don't know where. So we have to ensure the whole thing is within D. The second thing we have to check is the existence of a one-step feedback law at each XU along the trajectory we plan. So what is this feedback law? Well, remember, just because I'm inside the trusted domain at this time doesn't necessarily mean I'll keep staying inside the trusted domain as I execute my trajectory open loop, right? I could diverge because, again, I could wind up at any point inside this epsilon ball, and then at the next step, I could go even further from my trajectory, right? If I didn't have a feedback law. So we need a feedback law. And how are we going to do that? Well, I'm going to go over it very briefly, more details in the paper, but the central idea is that we're going to use perturbation bounds on least squares, and we're going to compute our control command with least squares. So let's start out in a very simple way here. So you have some x over here, and you want to go to some x desired, and you have some controller that'll compute u for you. This is the standard case when you know exactly where you are and your models are valid, right? But what's actually going to happen when we execute our trajectory is we will never get to our planned x point. We'll get to somewhere within epsilon of x, and that will be some point x tilde, okay? And so now we need to figure out a way to get from x tilde to the x desired, right? So how can we do that? Well, we have to apply some kind of feedback control that looks at the deltas between basically where we ended up and where we thought we would be, and correct for those when we try to go to x desired, right? So those deltas that you see there actually are also bounded. How do we bound those? By getting more Lipschitz constants. How do we get Lipschitz constants? We just talked about that, right? We use that FTG theorem, we do the fit and the KS test and so on. So we can use the same exact process to estimate these Lipschitz constants, LG0 and LG1, that are bounding those deviations delta. Then what we can do is rewrite this equation in a kind of nice way for least squares and set this up as a constrained least squares problem where we have to pick a control command u tilde that will optimize that equation there. So this is not anything new. We're not doing anything that hasn't been done before. We're just framing this as a least squares problem. And then using a previous result, basically directly from here, we're again not doing anything new here, we can have perturbation bounds on that result, which tell us how much the least squares solution changes as a result of model error. Again, nothing new being done here. But what we can say is that if we select our command u so that this bound is satisfied, then the feedback exists. And this is what we have to check at every XU that we generate. We have to check if we can in fact compute that bound. So if you can, and you have this feedback law, then the planner is guaranteed to stay where the model error is low, and the system will be stabilized in execution. So here's a quick animation of how the planner actually works. So I've plotted the x component of that trusted domain D here. And that's in brown. And so I'm starting at some state, and I want to go to some goal region. There's some obstacles in the world. So as I start to plan, I'm going to start sampling different control commands and getting to different states. And again, I have to check if that epsilon ball is around that state I just sampled is within R set D. If so, then I keep it. If not, I reject it. I keep sampling. I have to check if my U is within bounds that are determined by that feedback controller stuff on the previous slide. If so, if not, I reject it. And I basically keep sampling and building the tree. I also have to keep checking if I am within epsilon of an obstacle, right? And if I am, then I can't guarantee safety, right? So I have to reject those, and I continue planning until I reach the goal region. So from this, you can pretty clearly extract a trajectory, right? Once you have the trajectory, you actually need to execute it in the real world. How do you execute it? Well, because you have that feedback law that's guaranteed to exist for every XU on that trajectory, we simply apply that feedback law. So we take a first step. We were trying to get to X1, but because we have the wrong dynamics, right? The true dynamics are F, the planning ones are G. We have the wrong dynamics. We end up to epsilon away from X1. So we at X tilde, we need to correct for that when we try to go to X2. But again, we don't get to x2 because we don't have the true dynamics. We get somewhere with an epsilon. We have to correct for that, and so on until we eventually reach an epsilon ball around the goal. So what can we say about this whole process on a theoretical level? It turns out we can make a pretty strong statement here, right? The first condition that has to be true for this statement is that the one-step feedback law has to exist for every transition along that trajectory. So we already checked that in the planner. The second is that the Lipschitz constants we estimate have to be valid, okay? If those two conditions are true, then we actually guarantee that the system tracks the plan with epsilon accuracy. And to put it really clearly about those Lipschitz constants, we need to estimate actually 3 separate Lipschitz constants. So the one on model error is the first, and then those Lipschitz constants for G0 and G1. If we estimate them all with confidence rho, then the probability that they're all valid is rho cubed. And so this is actually our bound here, or I should say guarantee, not bound here. Okay, so just to show a few quick experimental results, we tested on a 6-DOF quadrotor, fully actuated, and a 7-DOF Kuka arm. And we tested against open loop execution and also the naive kinodynamic RT, which just trusts G everywhere. That's kind of the standard approach. And again, the learned dynamics were created with a very simple neural network, just one hidden layer. So this is execution on the quadrotor. In red, you see the nominal plan. In green, you see an open loop execution. And in blue, you see the closed loop. And you see that the green and the blue are actually fairly close together. So you might say, well, why do we need that closed loop? And that's true, but remember that they're close together because we're staying in the trusted domain where our dynamics are actually valid, right? So you would expect the open loop to do pretty well. In some cases, it can leave that domain, though. So we really want that guarantee, and so we want the controller. Here's an example of naive RT. It's a disaster, right? The naive RT plans this red trajectory, but it cannot track the trajectory even with the closed loop controller because that trajectory completely exits the trusted domain. There's not really much you can do after that. Here's an example on a 7-DOF Kuka arm. This was simulated, so we never knew the dynamics here in closed form. They're all inside MuJoCo. And the arm is trying to move from under the table to over the table. Again, what you see here, open loop and closed loop both do well. You'll see in the numerical results, closed loop does a little bit better. But they both do well here. And this is also a case where we don't sample the entire configuration space of the arm. As I said at the beginning of the talk, it's really impractical to sample these high-dimensional spaces and cover them. In fact, what we do is we collect several demonstrations, and then the data around those demonstrations basically becomes the trusted domain. So you don't have to cover the entire space. You can do a much more targeted sampling. Here's the naive kinodynamic RT. And as you can see, things go pretty badly pretty fast. This is, I'll be honest, the worst one we found. I show the video for emphasis. It doesn't always do this badly. But yeah, you can see what happens if it makes an unintended collision. It drops the tracking of the trajectory, and it's a disaster. Numerically, what we can see basically are two things. The first is that the naive RT does very, very poorly, as you could surmise from the videos. And the second is that the one-step feedback law is actually important for reducing your error and the variance in your execution. You can see with the one-step feedback law, we get much lower variances, especially for this case, than we would without it. Okay, so in summary, what this work has shown is a way to estimate a Lipschitz constant in a trusted domain, and then, of course, to estimate the domain itself for use in motion planning. And if these are estimated correctly, the motion planner is guaranteed to reach the goal with some desired probability that you use to estimate those Lipschitz constants. And this was applied to fully actuated high-dimensional systems, quadrotor arm. Yeah, Russ?
So I love the setup and all the steps, but it feels like it's bleeding conservatism. And I worry that for any real system with any noise, for instance, in your sensors, it's going to shrink your Lipschitz like crazy, or and balls fitting in balls. At some point you're just not going to be able to find any plans, right?
Right. So Russ's point is that with noise and real-world systems and so on, we're going to need to make those Lipschitz constants really big to account for all that stuff, which means our radius of our balls shrink, and then we become too conservative. Yeah, absolutely, I agree with that. I think, this does make sense when you have some kind of filter on your perception to make sure it's reasonable. If it's really noisy, I don't think you'll be able to do this. But on the other hand, keep in mind that since this is planning for, let's say, a robot arm, I mean, you are going to be able to get the joint positions of the robot arm fairly accurately. For a quadrotor, getting its pose in sixth off, maybe not so much. Yeah.
Even though the balls in the balls is you're giving a lot of conservatism in order to make that work.
That's true. That's true. But if you make your radius big enough, right, by growing in the way that I showed, I mean, you can see it actually works pretty well in practice. So, yeah. But of course, sensor noise will make this worse. Yes. So anyway, this was applied to these fully actuated systems. That's really limiting, right? And I just really want to mention that, just very briefly, that we have gone beyond this in recent work. I'll just talk about this very quickly. So Glenn here has found a way to make a spatially varying R, and he has found a way to use a much more sophisticated controller that uses a learned Riemannian metric and contracts with that. And this has allowed us to extend this approach to underactuated systems as well. So for instance, here is an underactuated quadrotor model that's executing a trajectory we planned with learned dynamics. Here is a rope dragging task where we're pulling the head of a rope and we want to get the tail to some region. This is massively underactuated, and it's a 22-dimensional state space. We again use demonstrations for the data here and learn the dynamics around those. But still, you can guarantee that this gets to the goal, even in this enormous state space. Right? Okay, so that was the work on learning to avoid the model's mistakes by basically making guarantees about where that model was valid. But now I'm going to shift gears a lot, and I'm going to say, well, in that work, we at least knew the state space we were dealing with. We may not know the model exactly, but we know the state space. What about when you just have images, right? You don't really know the state of the system. Of course, there's been a lot of machine learning work that learns from images, but the issue with that is that it tends to be pretty data inefficient. So can we use some domain knowledge in the form of a simple model to really rein in that data inefficiency? And when we're talking about simple models, I just want to say that if you're a roboticist, you're probably already doing this, right? In some form, kind of implicitly in your mind, right? You model a car maybe as a kinematic bicycle. You model a humanoid as a linear inverted pendulum or a more sophisticated inverted pendulum. You model an arm as a series of links and idealized joints which have no friction and no dynamic properties. You can just move them wherever you want, right? We know that this is not the real world, right? But these models are still incredibly useful. We've even developed models like this for cloth to treat it as an elastic band instead of a cloth for the purposes of planning. So we do this all the time, right? So the question is, how do we apply that kind of thinking when we're doing things from images instead of specifying this state? So this is the work of my student Tom Power, and Tom was interested in solving this problem that seems almost impossible when you first look at it. So again, you want to plan a sequence of commands, use, that get you to some goal, but the dynamics of the underlying system are actually unknown. Okay, well, we can maybe learn some dynamics, but now the state space of the underlying system is unknown. What do you do then? Well, you have to go with images, right? So this is a system that we experimented with. We call it the tethered mass. It's basically a bowling ball on a rope, right? And you can see the dynamics of this are incredibly complicated, right? So let's say we have high-dimensional observations, images, RGBD images, and so on, of these kinds of systems. We're also going to assume that we have access to the goal region. So we know what it looks like to achieve the goal. And in these kinds of examples for this system, it means moving the mass to some location in space. So our objective is then to complete a given task specification with as little interaction time on the true system as possible. So I want to use prior knowledge, I want to use images and so on of related systems, but I really am trying to limit the amount of online data that I collect. Why do we want to do this? Because if we ever want robots to work in unstructured environments, they have to be able to learn quickly, right? If you bring a mug home to your kitchen robot, and the robot needs to manipulate that mug for a day before it can pick it up reliably, well, first of all, it'll break it, but second, that's just not going to be very useful, right? So we need to learn quickly with little online interaction. Okay, now, as I said, we have this domain knowledge in the form of a simple model. And what this simple model is a coarse approximation of the system state Z with some known dynamics function F, okay? Now, what do I mean by coarse approximation? Well, let's take a look at these two videos, right? On the left, you have a cart pole model, which I'm sure you guys have seen in your controls course or in other kind of benchmarks. So this cart pole model is definitely not a tethered mass, right? We know that. But it turns out that the tethered mass sometimes does behave like a cart pole model. I mean, just watch how it swings back and forth. You could kind of approximate this as a certain cart pole with certain parameters, right? Now, the problem is, though, we don't know where such an approximation would be valid, right? And so that's what we actually have to learn. We have to learn where we can approximate the state of the true system, which we don't actually know, with the simple dynamics model. And our goal has to be reachable using states and actions where this approximation model, where this approximation is accurate. So I want to say that in future work, we're going to pick this simple model automatically, maybe even synthesize it online from a collection of other simple models. But for now, we are determining which simple model to use for a task manually. So that's a limitation of this. But building on this machinery, I think we should be able to do it automatically. So the method that we presented is called LVSPC, and the key insight behind this method is that we should trust the dynamics predicted by the simple model when they produce visually similar results to what the complex system is actually doing. So if I see the complex tethered mass rocking around like a cart pole, I should think, hey, the cart pole model might be a good approximation of the dynamics of the system. Okay, so what does that turn into in action? It's very complicated. Okay, there's a lot of moving parts, and I don't have time to go into everything. But I'll go over it at a high level. So the method starts with a pre-training phase where we only know about the simple model. So we never see the true system here. So we only see cart poles, no tethered masses here. And we basically learn a perception system, right? We learn how to estimate the state of the simple model from rendered images of that model. We can do all this in simulation. One caveat or wrinkle here is that we actually don't just estimate it one time, we estimate it multiple times with an ensemble of CNNs. That gives us a measure of the uncertainty of our prediction. So the things that don't look like this simple model will have a high variance in the prediction of that ensemble. That's very important because online we'll be given images not of the simple system, but of the true system. And when those images look similar to what we've seen in training, basically look like the simple model, our ensemble's output will have a very low variance, meaning we can say, oh, it's a fairly good approximation. When that's not the case, the variance will be very high. So from that, we get the state of the corresponding simple system for the complex system's images. We filter that state and we do motion planning on it using MPPI, which is a trajectory optimization method. But both the filter and MPPI require transition dynamics, basically the probability of getting from one state to another in order to work. And we learn those transition dynamics online, as well as do system ID for the simple model online. And we do that using a zero-mean Gaussian process. Basically, at a high level, what you can think of this doing is estimating the noise in a certain transition when executed by the simple model. So offline, this is what the system looks like, just an example for this tethered mass. These are different cart poles rendered with different thicknesses and ball sizes and all that. This is a kind of domain randomization. And we use this for offline training that ensemble. And then online, we encounter an observation of the true system. We estimate the corresponding simple state, and then we plan a trajectory in the simple state space to reach the goal. Here, the goal is to hit that blue dot with the mass. Okay, so a few experiments, and then I'll wrap up. So first, the 2D tethered maths, then I'll show you a bimanual rope manipulation task and compare LVSPC to some baselines. The baselines we looked at were state-of-the-art at the time RL methods. One was curl, which is a model-free RL method, and planet, which is model-based. And again, really what we care about most here is data efficiency. We know model-free reinforcement learning in the limit will learn the policy perfectly. That's not interesting for us. What we want to do is learn the policy well with a small amount of data. We also looked at some ablations I'm not really going to go into deeply. So for the 2D tethered mass, we're trying to hit a target with the ball on the end of it without touching that target with the rope. So that makes the task a lot harder. You can't just randomly swing that mass around until you hit the target, because you'll hit it with the rope first. And here's what it looks like when we're doing the online learning. So at the first episode, no method is actually effective. But by episode 5 or so, our method is starting to become more effective. Planet and curl, basically for all of this video, will be failing. They are not going to do much in this low data regime. But by episode 20, our method is actually pretty effective. And if you look at the plots here, our method is in blue on the left here, and it gets to, I'd say, 85, 90% success after only 20 tries. Remember, it has never, ever seen a tethered mass. All it's seen are carp poles. And just 20 tries later, it can do this task, which is pretty tricky, with 85 or 90% success. And on the right, you see comparisons to the baseline. Curl does the best, but it takes it an order of magnitude more tries to get the same level of performance as our method. This is the rope manipulation task. The goal is to place the rope center inside this narrow gap. This is kind of like a cable routing task you might want to do. And after 20 trials, our method can do it pretty reliably, again, greater than 80% success. Curl and planet are just getting started. Similar kinds of results, an order of magnitude more data is needed for curl, which is the best at this task to reach the performance level of ours, although curl does get asymptotically higher performance, as we expect from model-free RL. And then finally, the last thing I'll show, an experiment on the real robot where we are domain randomizing in the simulator, playing with background colors and textures and noisifying the data intentionally, and then running this on the real robot. We start out having almost no success. We get caught on these hooks, but then after, again, only 20 episodes, we get higher than 80%. To me, this is really impressive. This system has never seen a real-world image, and it has no idea what a rope is, right, when it starts. And after only 20 tries, higher than 80% success. Okay, so I'll skip the summary just for time here and just summarize the whole talk to say that I've shown you basically two methods that are tackling this problem of dealing with unreliable models. On the left, we had a learned model, and we learned how to put a bound on that model so that we could plan and guarantee safety. On the right, we didn't even know the state space of what we were dealing with, but we had a simple model that could approximate that object in some states, and we learned basically how to exploit that simple model to perform the task and avoid its mistakes in a data-efficient way. And in future work, I'm really interested in merging those two methods. Can we actually put bounds and guarantees on methods that learn from images? Really tricky, but I think it might be possible. And also, can we get the best of both worlds of things like model-free RL and our more model-based methods so that it gets pretty good with a small amount of data, but in the limit, it is going to be really an expert. So with that, I'd like to say thank you to my awesome students who did all the work that you saw here today. They really make coming to work a joy, and I love just doing this research with the students I have. And I'll open it up for questions. Thank you.
I thank you for the great talk.
Thank you.
For the first part of your talk, when you decided to trust regions, you kind of make a binary decision on whether you should trust your model or not. But shouldn't that be kind of a continuous decision of, like, for example, you could cast weight RT based on how far you are from available data? I just wanted to hear what benefit the trust region method has over like a soft decision?
Yeah, great question. So do we want just this binary decision of trust, or should it be more continuous? So you're totally right that you could say, how much do I trust my output of my network here? And then I could, let's say, bias the RT to things I trust more than others. The problem with that is that you can't put a hard guarantee on the trajectory that you produce. You might produce a trajectory that works great 99% of the time, but 1% of the time you're going to stray out of that trusted domain, and your feedback controller is basically going to be useless, and you are just not going to be able to get to the goal. And so the whole point of this work was saying, like, I want a guarantee that, if I estimate my Lipschitz constants correctly, then this trajectory will work. Yeah.
So I don't know, you had your hand up before as well.
Oh, sorry, I didn't see it.
Okay, thank you for a great talk. I have a question regarding the second paper. So basically, you first train your model on the simplified dynamics, and it's also on pixels on the similar simulator. I'm wondering, did you ablate if your high sample efficiency coming from pre-training on that stage? I mean, it seems that I guess like if you train curl or like PlanNet on the in the environment, I guess you don't pre-train them and just count the episodes.
So I went really quickly through that part, so I didn't have time to mention that we actually tried exactly this, that we pre-trained both of those on the simple model data, and basically it didn't do much. When it started encountering the new images, it basically unlearned all of the things that it had learned from the simple model images, and it just kind of started from scratch. So yeah, we did try that, and it did not change things.
I see. Is the curl with default the original SEC backend?
Yeah, so we got the code that was with the curl paper, so we used whatever.
I see. Yeah.
And I mean, if you think about it, right, like, can you ever expect a model-free reinforcement learning method to learn something in 20 trials? I mean,
That's pretty
just
hard.
not
Yeah.
really feasible. Yeah.
Yeah, just sort of repeating as well. Really interesting talk. Thanks a lot. Sort of perhaps a bit of a naive question coming in. I apologize for butchering pronunciations to start out with. The Lipschitz constant that you came in. I'm curious. Is there any way when you're choosing D to guarantee that it's bounded, or is there a scenario that can be imagined where you're trying to create to perform this guarantee in a region where the real Lipschitz constant is unbounded, and so getting that reverse Weibull distribution is invalid?
Wrong. Yeah, great question. So where can we assume the Lipschitz constant is bounded? Okay, so let's try to understand what the Lipschitz constant is representing. So usually what you do for Lipschitz constant is you get a function, and you just basically are trying to estimate that bound on those ratios. But for us, it's a little bit different. I mean, it is a function, but the function is comprised of f minus g, right? So, which is encoded in samples from f and g, right? So that Lipschitz constant is basically looking at the error between f and g. So if that constant was infinite, that means that there must be a point where your model predicts negative or positive infinity or something, or the true system is outputs negative or positive infinity, because that's the only way that you could have that kind of ratio for two different inputs.
That's true of every linear system.
What's that?
A linear system would have that property.
No, I mean the Lipschitz constant of the linear system would just be.
The Lipschitz constant of A, but I think if you're doing A times X, then I guess it goes unbounded, right?
Well, no, remember, it's the Lipschitz constant of the error, right? So if I've so also the domain is bounded, I have to say, right? So, but it is the Lipschitz constant of the error, yeah. You're right.
But then in the case where you also have two other Lipschitz constants that you're estimating.
Yes.
And in that case, you're doing this.
Yeah, it's the same thing, but again, domain is bounded, right? So for the G0 and G1 Lipschitz constant, we just use that same trusted domain that we got for the LF minus G constant. Yeah.
Any other questions?
Thanks for the talk, Dmitry.
Sure.
I was curious where you were getting the data to fit the model for the manipulators.
Yeah. So are you talking about the first
The first
part?
talk, right?
Yeah.
Because if you like avoid singularities in your data set, then I guess your planner will, for free, learn to avoid kinematic singularities in properties like this.
Well, yeah, we didn't specifically try to avoid singularities. So what we basically did is provide demonstrations of going like this. And there were a couple demonstrations, then we sample around those. And that was our data set. Yeah.
On like the order of how many demonstrations is this?
I would have to check the paper for the exact number, but I think it was like 3 or 5 or so, but you'd have to check the paper to be sure. Yeah.
Cool, thanks.
Mm-hmm.
Yeah, thanks for the talk, Dmitry. So in the last experiment, let's say you randomized the textures on the pendulum or the cart pole, and you like flipped it up. You flipped the image upside down, and you did some like trivial transformations. So there's still it's still with a very simple function you can still approximate that. You just like need to unflip and undo some textures, and you can still represent the dynamics of the system, but it looks super different visually, right? So with but your ensemble will probably give you something nonsensical, right? So is that like a failure mode of that kind of method?
Yeah. So I think this is a really good point. When you do this kind of visual similarity stuff, you basically have to do domain randomization when you're learning your ensemble. Otherwise, even like a background object, right, will distract your network and the ensemble won't know what to do, right? So you basically have to do domain randomization. And I think that is actually a limitation, because the question with domain randomization is always, how do you know what to randomize, right? Do you randomize textures? Do you flip? Do you not flip? So in a sense, that is something that we have to determine to figure out what situations we will scale to. Yeah.
Thanks for your talk. In your second project, you are using Ensemble to, for example, to estimate the uncertainty of your model's predictions. Could we somehow also be using your first project to somehow use that kind of uncertainty estimation of your state space to construct the trusted regions to plan with?
Yeah, I love how you're thinking. And, maybe we should collaborate, because this is, okay. I don't know what happened, but I will get back to here. Did the screen die again? Okay. So anyway, this is one of the ways that I'm thinking about how to do this exact thing here. So you notice the ensemble is giving you an uncertainty, and before we were getting this uncertainty bound through Lipschitz, right? Now the problem is I don't know how to turn ensemble uncertainty into a hard bound or a hard guarantee, right? That's the main limitation there. Could you use it? Definitely, right? You could do an ensemble of those G networks and then look at the variance and then put a threshold saying, oh, if the variance is higher than this, then I'm not going to believe it. But where's that threshold, right? So I'm really looking for a way to bring those two things together, and so maybe I could get that threshold through some kind of Lipschitz estimation or something else. Yeah.
All right. Any other questions? If not, I guess I want to thank Dmitry for coming.